As the study of the atom continued, it was discovered that the electrons were the ones responsible for the chemical nature of that particular element. The way that this was discovered was through the use of what we call flame testing. This is where you take a sample of a particular element and you put it to flame. It was discovered that different elements would give different colors of light. So in this chapter, we're going to talk about the elusive electron, and we're also going to demonstrate how different elements will provide us with different colors of light when they are energized. So stick around. Now I'm going to perform flame tests on 4 chemicals. I have 4 chemicals in these beakers. Each of them contain 2 different elements. One of the elements in each of these beakers is chlorine, so that's not the one I'm concerned with. It's the other one, the partner of the chlorine in each of these, that I'm concerned with. This first one has sodium and chlorine, sodium chloride. The next one has strontium and chlorine, strontium chloride. This one has copper and chlorine, or copper chloride. And finally we have lithium chloride. So I'm going to take a sample of each one and allow it to burn in the flame and see if we get different colors to illustrate that the elements provide different colors in these flames. First, I'll burn a sample of the sodium chloride. Oh, we see a very bright yellow to orange color with the sodium chloride. Next, let's try the strontium chloride. With strontium chloride, we get more of a reddish color to the flame. How about the copper chloride? Oh, here we get a green color for the copper chloride. That's fairly easy to see even on the camera there. And then lastly, the lithium chloride. Oh, another really bright red color for the lithium chloride. Very red. So we can see that these 4 chemicals give off different colors of light when they are given energy or they're energized. So as more and more of these flame tests were analyzed, it was determined that the chemical behavior of these elements was due to the electron configuration, the way that the electrons were arranged in the atoms of that element. But to understand that relationship and the nature of atomic structure, first we need to educate ourselves a little bit on the nature of light. Visible light is just one part of what we call the electromagnetic spectrum. Electromagnetic radiation, it's a form of energy that exhibits wave-like behavior as it travels through space. There are all types of electromagnetic radiation, not just the type we can see. There are things like X-rays or microwaves or gamma rays even. But no matter what kind we're talking about, all electromagnetic or EM radiation is wave-like. So let's talk about waves for just a minute. Here are some characteristics that are common to all waves. I've drawn an example of a wave on the board here. A few things to note. One, the baseline is what we call the origin. If there were no wave at all, it would be simply a flat line. The top of the wave is known as the crest, while the bottom is known as the trough. Another characteristic of a wave is the height of the wave, if you will. We call that the amplitude. You could think of it in terms of the intensity of the wave. You can have amplitude this way or amplitude this way. It's simply the deviation from the origin that we see in the wave. But probably the 2 most important characteristics of waves that we're going to talk about are wavelength and frequency. The wavelength, simply put, is the shortest distance between 2 equivalent points on a continuous wave. We could measure it, for example, from crest to crest, like so, or from trough to trough. The point is it has to be 2 equivalent points on that wave. For instance, we could not say that the wavelength is from here to here. They look equivalent, don't they? They're both passing the origin, but this one is passing in the negative direction while this one's passing in the positive direction. To designate the wavelength in an equation, we use the Greek letter lambda. The frequency is defined as the number of waves that pass a given point in 1 second. 1 hertz is the SI unit of frequency. basically described as a wave per second. If we had a frequency of 750 hertz, it simply means that we have 750 waves per second. So when we're using frequency in our calculations, we use 1/2 as our units for frequency. Just like we did for wavelength, we also use a Greek letter to describe frequency. This letter is the Greek letter nu. So wavelength is expressed in meters, and frequency is expressed in hertz, or 1/2. One more thing. All EM radiation, including visible light, travels at about 2.998 times 10 to the 8th meters per second, in a vacuum that is. That's roughly 300 million meters per second. We can actually represent the relationship between wavelength and frequency using this equation. The speed of light, c, equals wavelength, lambda, and frequency, nu. Speed of light equals wavelength times frequency. And remember, the speed of light is always around 3 times 10 to the 8th meters per second. So, if we have the wavelength, we can always find the frequency. Or, if we have the frequency, we can always find the wavelength. Even though all EM waves have the same speed, they can have different wavelengths and frequencies. And this is the relationship between the two. We find that there's an inverse relationship between wavelength and frequency. What we mean is, if we have a higher wavelength, that means that same wave has a lower frequency. Or, if that wave has a low wavelength, then we have higher frequency. You get it? What I'm holding here is called a spectroscope. And this spectroscope has a little tiny prism inside. There's a viewing hole here and a small slit here. If I hold the spectroscope up to, say, sunlight, the sunlight will pass through the little slit and through the little prism inside, and then it will be dispersed into a continuous range of colors. White light does the same thing when it passes through a prism. So these are the colors of the visible spectrum. You get the same effect when you see sunlight pass through little droplets of water in the sky to form a rainbow, right?
Come on, man, my turn.
No, not yet. I'm still not done.
Well, at least fix my jaw.
The interesting thing is that the visible light that we see is actually a very small part of the complete electromagnetic spectrum. We can see everything from radio waves on this end to gamma rays on the far end over there. You can see though that that little sliver in the middle, when we expand it, it shows us the visible colors of light that we see. Red, orange, yellow, green, blue, indigo, and violet. We call it Roy G. Biv for short. As we view this picture from left to right, the part that we see over on the left are very, very large wavelength waves, but with very, very small frequencies. But when we go to the other side, we're talking about waves that have very, very small wavelengths, but extremely large frequencies. Remember our relationship, the inverse relationship between wavelength and frequency. So, on this end, large wavelength, small frequency. On that end, large frequency, small wavelength. One more thing. Energy is directly related to frequency. Think in terms of the ocean. If I was being hit by waves in the ocean, the more waves that hit me in a short period of time is going to be more energy, isn't it? But if it's just a few waves every now and then, that's a lot less energy. So, the more frequency we have, the higher the energy. Thus, radio waves are extremely low in their energy, while gamma waves are extremely high in their energy. So when you hear someone talking about the red end of the spectrum, they're talking about lower energy, higher wavelength. If they're talking about the blue or violet end of the spectrum, they're talking about higher energy, lower wavelength. And remember, since all EM waves travel at the same speed, we can use the formula C equals lambda times nu to always find the wavelength or the frequency of any wave. Just to fill in your perspective a little bit on the different types of waves, again, we have radio waves on this end of the spectrum, very low energy, very large wavelength. Some of them have wavelengths that are measured in miles. That's how big they are. Then we have microwaves, as you can see, followed by infrared. Then we pass into the visible spectrum. The red end first, followed by orange, yellow, green, blue, indigo, and finally violet. Then we see the ultraviolet part of the spectrum, followed by X-rays, and then finally gamma rays. That's all we're going to cover for this video. We began our time by talking about flame testing, how flame testing allowed us to understand that different elements have different electron configurations, and it's those electron configurations that control the chemical nature of that element. Then we talked about waves and the different parts of the wave, focusing especially on wavelength and frequency. We showed the relationship between wavelength and frequency using the speed of light. That is, that c equals lambda times nu. The speed of light equals the wavelength of the wave times its frequency. We talked about the inverse relationship between wavelength and frequency. That is, when wavelength goes up, frequency goes down, and vice versa. And then we spent some time on the electromagnetic spectrum, showing the different ranges of the spectrum, including the range that we see, visible light. We'll continue our discussion of light and how it relates to electrons in the next video. Until next time, God bless.